Hello everyone. Today we will continue the previous study on the branches of holomorphic functions, how to define it, and how to use define the branch holomorphic functions to study the definite integrals. More precisely, today we will focus on the following one example. So how to compute the integral from 0 to 1 over x to alpha's power times 1 minus x to 1 minus alpha's power with alpha between 0 and 1. And before we carry out the computation, we first look at the index alpha. This is very important. And first noted that we should understand the integral I in the following way. Limit epsilon 1 goes to 1 plus, epsilon 2 goes to 0 plus, limit epsilon 1 minus epsilon 2. We should understand in this way because when x is 0 or 1, the integrand is not well defined. It blows up. So if you look at the picture, so this is x, this is the integrand 1 over x alpha times 1 minus x 1 minus alpha. So 1. Kind of like this. Okay, but by the p-test, we are able to determine that this is convergent because near 0, 1 over x alpha, 1 minus x, 1 minus alpha is has the same growth rate as 1 over x to alpha's power because the second factor is bounded below by, for example, 1/2 when x is small. Okay, and similarly near 1 over x alpha, 1 minus x, 1 minus alpha, the first factor is bounded below. Therefore, this is same as 1 over 1 minus x, 1 minus alpha. Okay, then near 0, so for example, let's do 1/2 to epsilon 1 to 1/2, 1 over x alpha. This you can integrate it is negative 1 over negative alpha x to 1 minus alpha 1/2 epsilon 1. Okay, and then you notice that since alpha is less than 1, this is bounded. When epsilon 1 goes to 0 plus. And similarly, if we look at the integral 1 over 1 minus x to the 1 over 1 minus alpha's power, this is minus 1 over 1 minus alpha, and 1 minus x to alpha's power. One minus epsilon 2. And when you plug in, you see it's bounded when epsilon 2 goes to 0. Here, the alpha, the 1 over 2 is not that important because no matter what value you take, you can take 1/3 or whatever. You plug in, it's always a constant. The the thing we need to care about is epsilon 1 and epsilon 2, because you need to take a limit. You have infinite many numbers to bound, so it's not always constant. But in our case, since we assume alpha is between 0 and 1, the integral is well defined. And immediately, by the same argument, we will see that when alpha equals 0 or 1, the integral does not exist. It goes to infinity. Okay, now let's solve this problem solution. First, we fix the function fz, which is z to minus alpha 1 minus z to minus 1 minus alpha, or it should be, if you would like, you can write alpha minus 1, but I would like keep it as this. Okay, then of course first thing we need to do is take the branch. So for z to minus alpha, we write it as e to negative alpha times log z. Okay, then we need to take a branch for z. So for log z, as usual, we cut the domain along the positive axis starting from 0. I would like to make it longer. Okay, then your domain is everything except the positive real number line, including the origin. I mean, the set you get rid of include the origin. Okay, then you need to take a branch. Take a branch means you need to give the region for the angle part, because we know that for log z, you have two parts. One is log z norm, the other one is I theta. Okay, so if you so here theta, we take it to be any number between 0 and 2 pi. Then the formula, you can read it off. So assume z is r e I theta, then z to negative alpha. So where theta is between 0 and 2 pi. And then this power function is given by r to negative alpha times exponential negative alpha times I theta. Or if you like, you can write I times alpha theta. This is because your choice of the branch. So this is choice of the branch. This is the final formula we are going to use in the following for z2 minus alpha. And similarly, for 1 minus z minus 1 minus alpha, we rewrite as exponential negative 1 minus alpha log 1 minus z. Then we need to take the branch for log 1 minus z. So here, for convenience, we take the following branch for z. So here you have point 1. You get rid of the line on the half line on the real axis, on the axis starting from 1 to positive infinity, and then your domain is the remaining part. Okay, and now you need to write down the angle. So here we suppose 1 minus z is rho exponential I alpha, and we take alpha to be a number between negative pi to pi. Why this is negative pi to pi? Because here you have 1 minus z, so you don't have value for any real number larger than 1 for z. Therefore 1 minus z cannot be negative, so you can miss a pi or negative pi angle here. So this is a z diagram, but if you look at 1 minus z, then what you have is exactly the other cutting for log function. You get rid of the negative real number line. Okay, then 1 minus z minus 1 minus alpha's power is given by rho minus 1 minus alpha times exponential I negative I 1 minus alpha times phi, and of course phi is between negative pi to pi. Okay, so this is the first step. You need to define the branches for z to alpha's power 1 minus z to 1 minus alpha's power separately. So naively, we should get rid of the two slits on the z-plane. But then if you look at this case, the union just a line from 0 to infinity, and for the remaining plane, how to construct a loop, how to construct a contour, it's difficult because the one you are interested in is a real number line from 0 to 1, so you need to have some paths like this. Okay, but then how do you construct a loop in the yellow part without canceling this part? So no matter how you do, if you want to close up, finally you need to come back. Okay, so this is kind of difficult because then you lose the control of this part, hard to control. Because the outside circle not going to infinity. So you have some, you don't concentrate all the interested property into the sum. Okay, hard to control. So the idea to overcome this is you noted that alpha plus 1 minus alpha is 1. That is to say, if you cross 1 to power to infinity, the angle changes 2 pi, then exponential 2 pi I is 1. What does this mean? This means no ambiguity. So this is the observation. Then next we will show that we can define a branch for 1 over z to negative alpha 1 minus z to 1 minus 1 minus alpha on a slightly larger domain c minus 0, 1. So if you draw a picture, we only get rid of this part because that part is good. So this will be our cut, our domain. Okay, now next we will rigorously prove this. So lemma z negative alpha 1 minus z negative 1 minus alpha defined as above in a smaller domain c minus 0 to positive infinity has a continuous extension to c minus 0, 1. This is the first step, so let me call it lemma 1 and proof. So recall that so first we need to define the value on the we first define okay, so denote define fz equals z to negative alpha 1 minus z to minus 1 minus alpha when z in c minus 0, 1 and x to negative alpha times x minus 1 to minus 1 minus alpha times exponential negative I alpha pi plus I pi for x in 1 to infinity, positive infinity. And it suffices to show that f is continuous at each point x in positive infinity. Okay, then take z near, so fix a point x, fix x in 1 to positive infinity. Take z near x and the imaginary z greater than 0. So what does this mean? This means we are interested in the line from 1 to positive infinity on the x-axis, and now fix the point x. Now you approach x from above, any point z from above. Then let's compare the value fz and fx. Then z to negative alpha times 1 minus z to negative 1 minus alpha. We plug in the formula introduced above. Delta 1, delta 2. Be careful that this formula will be used repeatedly in the following. Z to negative alpha 1 minus z to minus 1 minus alpha times. Okay, then the angle part, you just plug in negative r alpha theta times exponential I a negative 1 minus alpha times phi. Okay, since x is greater than 1, when z goes to x, we know that theta, angle theta goes to 0. This is because the angle theta is this one. Suppose z is here. Angle theta is this one. So when z goes to x, theta goes to 0. And what is the angle? The angle phi. Notice that the angle phi is this one. This is your phi. Okay, so when z goes to x, the phi goes to negative pi. This is a little bit tricky part. You need to be able to derive the limit. Okay, then limit z goes to x, imaginary z greater than 0, z negative alpha 1 minus z, alpha minus 1 is x minus alpha 1 minus x alpha minus 1 times exponential I alpha minus 1 times negative pi, or 1 minus alpha times pi. So that's exactly which is fx. Okay, and now let's compute the lower half plane. So when imaginary part z less than 0, and then by the formula, we still have the branch formula. The form is the same. And then when z goes to x, then theta. So now we have the graph like this, z. So the angle phi is this one. Angle theta is all the way around to this one. This is theta. Okay, then when you take the limit from below, you have theta goes to 2 pi, phi goes to pi. Then you plug in you have limit z goes to x, imaginary z less than 0. The limit of the function is x to negative alpha 1 minus x to minus 1 minus alpha times exponential negative I alpha times 2 pi exponential negative I 1 minus alpha times pi. So which is x to negative alpha 1 minus x to negative 1 minus alpha times exponential I so negative, let's see what's 1 minus alpha pi. Here a little bit tricky. Actually, what do you have? If you directly sum them up, you get exponential negative I sorry, not negative. It's I negative 1 negative alpha times pi. But exponential I 2 pi is 0. So exponential I negative 1 negative alpha pi equals exponential I 1 minus alpha pi. So as we intuitively showed before, this formula comes from the fact that when you cross 1 to positive infinity, the angle changes 2 pi. So exponential I 2 pi, which contributes to constant 1. Okay, then this is also fx. So we show the continuity of the function f. Okay, then by Morera's theorem, fz defined as above on z minus 0, 1 is a holomorphic function. Now we can go back to the original integral, the real integral. So good news is that now we can construct a better contour. So inside you construct contour like this, and then you also have outside one. Which is a circle with radius capital R. I call it CR. And the inside you have let's also give the orientation counterclockwise. Let's call this gamma epsilon, because here the half circle has radius epsilon. Okay, then by notice that this function is holomorphic. Then by Cauchy-Cousar theorem, we have the integral along the outside circle of the holomorphic function equals the integral along the inside circle, not circle, inside loop. Okay, then let's look at the inside one. We split this into 4 pieces, and from the definition you can see how we draw the loop precisely. So first you have from 0 to 1, so that's a horizontal line below the real axis. You see, just like last time, you see here x is from 0 to 1, y coordinate is negative epsilon. Therefore, we have this formula. You replace z by x minus I epsilon. And for the horizontal line on the above, you reverse the orientation. So minus 0 to 1, z is x plus I epsilon. Alpha 1 minus x plus I epsilon 1 minus alpha. And now for the circle on the right, from the orientation, theta is from negative pi over 2 to pi over 2, and you have parameterization epsilon exponential I theta, and in the denominator you have 1 plus because this half circle is centered at 1, so you should replace probably I should say z is 1 plus I exponential I epsilon. That's the parameterization we use here. 1 minus 1 plus epsilon exponential I theta 1 minus alpha, and plus or minus because you reverse the orientation right now. Okay, first let's write plus. And so for the left part, your parameterization is z equals epsilon exponential I theta. Okay, then you have d epsilon exponential I theta over epsilon exponential I theta to alpha's power times 1 minus epsilon exponential I theta to 1 minus alpha's power. So the angle is from pi over 2 to 3 pi over 2. So let's call this as J1, this second one J2, J3, J4. Okay, first, now we need to estimate J1, all those subintegrals. So first, the norm of J3 is bounded by some constant times the integral from negative pi over 2 to pi over 2, and inside you have epsilon exponential I theta times I, absolute value d theta divided by when epsilon is small enough, so the first term is bounded by 1/2, and the second term is bounded by epsilon to 1 minus half. So finally, it's all order epsilon alpha's power when alpha goes to 0. Okay, and for J4 similarly is bounded by so I will be sloppy. This is O capital O epsilon 1 minus alpha. Okay, next we want to consider the J2. So first, for J2, we plug in the formula for the branched holomorphic functions. So J2 is integration, negative integration from 0 to 1 dx and square root x squared plus epsilon squared alpha times exponential I alpha times arctangent epsilon over x times square root 1 minus x squared plus epsilon squared to the 1 minus alpha's power exponential I alpha minus 1 times arctangent epsilon over 1 minus x. So the only thing we need to take care is angle part. So let's look at this. Because J2 is the line in the above 0, 1. So the angle for theta is just this one. And the angle for phi, so recall that 1 minus z, negative 1 minus alpha is 1 minus z minus 1 minus alpha times exponential negative 1 minus alpha I times phi. So here we assume 1 minus z is rho exponential I phi. Phi is between 0 to negative pi to pi. This is a delta 2, formula delta 2 here. Okay. So what's the angle for so angle phi is 1 minus z, so this angle. One minus z. This is your phi. So it's a negative thing. Okay, and so therefore phi should be negative arctangent epsilon over 1 minus x. So how to derive this? Because you draw a perpendicular line, so this will be 1 minus x, so the height is epsilon. So the angle is arctangent epsilon over 1 minus x. So phi is negative this. Okay, probably I should write in this way to indicate this fact. Okay, then next, Next, we make the following claim, lemma. Note that J2 is a function dependent on epsilon. So limit epsilon goes to 0 plus, J2 is negative I. So I is the original real integral. Okay, now let's prove this. So here is also technical part, but the main idea we introduced the last time when we do some brutal estimate, we need to take some small scale which is larger than epsilon, but still very small. So similarly here, we cut the whole interval from 0 to 1 into 3 pieces, 0 to epsilon alpha prime plus epsilon alpha prime to 1 minus epsilon alpha prime plus 1 minus epsilon alpha prime to 1. And inside, we just have the, bad notation, this is J2. Inside is integrand here. Yeah, I'm lazy, so I just keep it here. Okay, so for first one, let's of course here alpha. The key point is alpha prime is greater than alpha, but still less than 1. That's a scale we want to explore it. And then we estimate the first term, x squared plus epsilon squared to alpha's power exponential I alpha arctangent epsilon over x times 1 minus x squared plus epsilon squared to 1 minus alpha's power exponential I alpha minus 1 arctangent. So what's the angle? I forgot. Yeah. Arctangent epsilon over 1 minus x. Okay, now if you the integrand, okay, so the norm of the subintegral is less than c times integration. C is a constant, and note that here this is bounded about by 1/2 to 1 minus alpha's power when epsilon is small, and the norm of this is 1, norm of this is 1, therefore it's bounded totally by 1 the integral of x squared plus epsilon squared to alpha's power. And then you can shrink the denominator to epsilon square. Okay, so this is bounded by epsilon square square root to alpha's power. So totally, the interval is epsilon alpha prime. So totally, you have the subintegral is of order epsilon alpha prime minus alpha. Similarly, we can conclude that for the third integral is also of order. Okay, let me step by step. x squared plus epsilon squared to alpha's power exponential I alpha arc tangent epsilon over x square root 1 minus x squared plus epsilon squared 1 minus alpha times exponential I alpha minus 1 arctangent epsilon over 1 minus x. Okay, then this one is bounded below by 1/2 to alpha's power. This is 1, this is 1. And so if you make a substitution, so this is bounded by c times, you change to y integral. Y is 1 minus x. Then the integral is from epsilon alpha prime, 0 to epsilon alpha prime, and the inside is y squared plus epsilon squared square root and 1 minus alpha. So similarly, you enlarge the denominator part to epsilon square root of epsilon squared 1 minus alpha. Then this is bounded by c times epsilon alpha prime divided by epsilon 1 minus wait a moment. Okay, so it's right. Then it's order O epsilon alpha prime plus alpha minus 1. Okay, so when we choose alpha prime, we need to make sure alpha prime is greater than alpha less than 1, and alpha prime is greater than 1 minus alpha less than 1. Otherwise, this estimate is useless. But of course, since alpha is between 0 and 1, we can always choose such alpha prime. Okay, now for the second one, basically we'll do the same thing. Arctangent epsilon over x square root 1 minus x squared plus epsilon squared 1 minus alpha exponential I alpha minus 1 negative positive arctangent epsilon over 1 minus x. The angle exponential part not important at this moment, but then for the next J1 part, the angle is important because they will give you some phase shifting. Okay, when you plug in, so how to bound this one? And let's look at this. This is bounded by 1. This is also bounded by 1, and for those parts, we do the following trick. We factor out x, so you have 1 plus epsilon x squared to the alpha's power, and also factor out 1 minus x, so square root 1 plus epsilon over 1 minus x squared to 1 minus alpha. Okay, then notice that epsilon over x is very small. because it's less than or equal to epsilon over epsilon to alpha prime, which is epsilon 1 minus alpha prime. And also epsilon over 1 minus x is smaller than epsilon alpha prime as well. Okay, then for these two parts, we can do the Taylor expansion. So basically this will be less than or equal to constant times, here you have constant. Constant times integration epsilon alpha prime 1 minus epsilon alpha prime 1 over x to the alpha's power, 1 minus x to 1 minus alpha's power, and times 1 over 1 plus O epsilon x times 1 plus O epsilon over 1 minus x. Or you probably you can just replace it by O epsilon. O epsilon 1 minus alpha prime O epsilon 1 minus alpha prime dx. So that's the crucial part. You have this, and then if you take the limit, okay, sorry. Here we are not doing. Oh, my bad. Yeah, here we are not doing estimate. We want to do the exact limit. So we also need to take care of the exponential part. So for this part, because epsilon over x and epsilon over 1 minus x is small, we can also use Taylor expansion for the angle part. And here, so therefore you have the angle part, exponential I alpha arctangent epsilon over x times exponential I alpha minus 1 arctangent epsilon over 1 minus x. Therefore, you will have here, you do the Taylor expansion for arctangent. So it's epsilon over x and then exponential part. So let's repeat. Here you should have more small terms. So actually, we can combine this to fourths. Exponential I alpha arctangent epsilon over x. This is 1 plus alpha arctangent epsilon x plus O epsilon over x squared. And then it's 1 plus O epsilon over x. And since epsilon over x is O order epsilon 1 minus alpha prime, then you have this. Similar for the other part, then you have this. So all everything is the equal side. Okay, so finally, let epsilon goes to 0 plus J2, J2 recall that J2 is negative this integral, so if you want to keep it, so the negative J2 goes to I. So that's the end of the lemma. Similarly, we can deal with the J1 part. So J1, the first step is to write down the branch functions explicitly. So dx x squared plus epsilon squared to alpha's power exponential I alpha 2 pi minus arctangent epsilon over x square root 1 minus x squared plus epsilon squared 1 minus alpha exponential I 1 minus alpha arctangent epsilon over x. So let's explain the angle a little bit here. 0 to 1. Now the line is underneath. We fix point Z. So for first part, the angle is given by this. So this is your theta. So what is theta? Theta will be 2 pi minus arctangent epsilon over x. So this is arctangent epsilon over x. And similarly, 1 minus z, the angle phi is this one. Okay, so you just keep it there. So 1 minus alpha arctangent. So this is exactly phi. And you see the only difference is that here you have actual 2 pi. The remaining part, if you take a limit, just like what we did before, so limit epsilon goes to 0 plus J1 is integration 1 minus x 1 minus alpha exponential I alpha times 2 pi. And we combine the left-hand side. So left-hand side of the Cauchy-Coushac, the corollary of the Cauchy-Coushac theorem, just this one. So the left-hand side, the right-hand side, the right-hand side, integration along gamma epsilon dz z to alpha 1 minus z to 1 minus alpha. If you take the limit, epsilon goes to 0, this is the real integral times exponential negative I alpha times 2 pi minus 1. Okay, next, let's look at the right-hand side, the circular part. So a small remark is the circular part is no more 0. It contributes some positive number. Okay, and so first, let's write down the branch function 1 minus alpha. So this will be norm of z to the alpha's power norm of 1 minus t to 1 minus alpha's power times exponential I alpha theta times exponential I 1 minus alpha phi. Okay, and then let's look at the angle phi. So what is the angle? So suppose you have a bigger circle and you have 0 and 1. So the usual parametrization will be z equals REI theta, and theta is between 0 and 2 pi. So this is theta. And the angle is, so the angle phi is this one. So it will be delta minus pi, where delta is this angle. Okay, then we can compute. So next we will compute the angle delta gamma equals delta minus theta. So this is gamma. So recall exponential I gamma is the angle of so the angle of 1 minus z divided by negative z. Or probably you prefer this form, z minus 1 divided by 1. Okay, now let's compute z minus. This is because of a meaning of complex number. So z minus 1 divided by z minus 1 divided by z is REI theta minus 1 divided by REI theta is 1 minus 1 over r exponential negative I theta. So it's 1 minus 1 over r cosine theta plus 1 over r I sine theta. So the angle will be arc tangent 1 over r sine theta over 1 minus over r cosine theta. So delta is given by this number. And, gamma is given by this number. And since r is large, so it's easy to see this is of order theta or sine theta over r. So when r goes to infinity, gamma equals delta minus theta goes to 0. So that's a property relation between phi and theta. Now we look at the integral along the outside circle. So first we can write down in the following form REI theta d theta after parametrization r to the alpha 1 minus 2r cosine theta plus r squared 1 minus alpha times exponential I alpha theta times exponential I 1 minus alpha phi. And now for the angle, you do a little bit trick. So for everything else, I keep it. Oh, for everything else, I can factor out r. So 1 over r squared, 2 over r plus 1 minus alpha, r to 1 minus alpha, r I e I theta d theta. And here you have e I alpha plus 1 minus alpha theta times exponential 1 minus r gamma. Okay, now you have cancellation. Alpha cancel out with this. EI theta cancel out with this. Okay, so when here you have phi minus. Here is phi minus theta. Okay, then simplify it. You have integration I d theta, and for this part is 1 plus O capital O 1 over R, and times. Then you plug in phi. Phi is what? Phi is delta minus pi. So here you have exponential I 1 minus alpha negative pi, and you have exponential I gamma. So this is, let r goes to infinity, we get uh, 2 pi I times exponential I 1 minus alpha pi. Therefore, combine the Cauchy-Coushac theorem, we know that the real integral dx x to alpha 1 minus x 1 minus alpha times exponential negative 2 pi I alpha minus 1 equals 2 pi I exponential I 1 minus alpha pi. So the integral, real integral, equals 2 pi I times exponential I 1 minus alpha pi over exponential negative 2 pi I alpha minus 1. We simplify it, we get this is negative 2 pi I over exponential negative pi I alpha minus exponential pi I alpha. And it's pi sine alpha pi. Okay, we are done. The formula is pretty beautiful. And it's easy to see when alpha is 0 or 1, the integral by the formula goes to infinity, blows up, because sine alpha pi is 0. Okay, I will stop here this time.